Hey, hello. leetcode72 added distance. This is a classic dynamic programming problem. We are given two string, word1 and word2, and we can do the following operation: insert, delete, and replace. Our goal is to estimate the minimum added distance from the word1 to word2. So here is one example. We have a word, horse. We want to get word Ross out of it, and the operation we can do is to replace H with R first, and then after that remove this R here. Then we will have the Ross here, and then after that the last step is to remove E. So with these three operation we can achieve. So this is the added distance. In our case, we should return 3. Whenever we handle a dynamic programming problem, the key thing is to figure out what's the subproblem and how we can derive our optimal solution from the subproblem solution. So let's jump to the content, see how we can divide that. Okay, now let's look at how we can divide this problem into subproblem and get our solution from it. So we have two examples here. This is example 1 and example 2. They both have a different situation that will give us different subproblem. So let me try to explain it. We use I here as a pointer for the first string and j as a pointer for the second string, right? So when we start from the beginning, in the first example here, I and j, they both point to the same character R here. So in this case, there's no edit required for us. We don't have to do anything for that. The I and j can proceed to the next one. So our final solution for this whole string, the final added distance, is equal to the subproblem, which is the added distance from this substring and to this substring. So from ORSE to OS. So if we can get the result of this added distance, then we have the global solution. So this is the way how we get from the subproblem solution to the global solution for this first situation. If we have a different character, like here, H and R, they are different, then in order to get our subproblem, we need to differentiate what operation we choose. If we choose a delete operation, that means we're gonna delete this H, and after that, in the string 1, the left string will be here. So we will move I to from I to I plus 1. And this is our source string now. But because we deleted, we haven't have anything have any letter meet the second string, so the second string j will still stay the same. So if we do the deletion, our subproblem becomes this string as our source string, and again the original target string as our target string. So this is actually the minimum added distance we want to calculate. If we could have this solution, this subproblem solution, then the value plus 1 will be our global solution. Because we have already did one edit here for the delete. Same thing apply to insert, because insert is also another option we have here, right? So we could have an insert here, meaning that we can actually insert R here to match the target R. Then we have the situation that the target substring now becomes OS, but the source string is still horse, because we haven't consumed anything from there. So this is our now new subproblem from here to this OS, right? So this is the reason why we have this formula for the delete. And the last option we have here is to replace. Replace means we delete the H and put R in the place of H. And because of that, we already have the situation is very similar to the first one, right? So now we both have R here. They both can move forward. I can move to I plus 1 and J can move to J plus 1. Now we have the same subproblem like the situation, like the example 1. So this will be our subproblem from ORSE to OS. If we have the minimum edit distance for that, then that value plus 1 will be our solution, I mean the global solution for this when we choose the replace, right? So our final goal for this is to figure out the minimum value from all these three options, and then we pick the minimum, and then plus make one plus, because no matter which one we pick, it's always count as one edit. So even though we managed to find the minimum, we still need to plus the one here, and this is actually the way how we compose our current solution from the previous subproblem. Okay, now let's proceed to look at the code, how we implement this minimum edit distance. We choose the method from the top down. So this is, we start by creating a memo. This is basically the way to remember our previous calculation. And as we mentioned before, that dynamic programming is basically a smart brute force. The way to being smart is to memorize the work we have done before, to reuse it to save the computation. And then this minimum function is our subproblem. We begin by giving I and j to 0 and 0, so that's our starting point. But then we recursively call this function to let it generate the solution for our subproblem. So I and j is the pointer to the array here. So in this case, if we have already moved here, that means all the beginning part has been consumed. We have already found the matching here. Then this function will return the minimum edit distance for the rest of the array for both. So first we check is the situation that if we consume all the letter in the string 1, then and the string 2 is not finished, then we simply need to return how many elements left. We can actually use the insert operation to make them the same. That's the reason we return this value as the length of the left string. Same thing apply to this one. This is the opposite situation. When we finish all the target string, we have already got our match, but the source string still have something left here. What we can do is simply return the length as our edit distance. Then the operation we choose is to delete, and we can delete them then to make them match. After that, it's always if we use the top down, then we have to make checked from the memo to save the computation. So if I and j in this space in this place has already been calculated before, then we can read it from the memo result. If it's not, then we proceed with our calculation, right? So the first thing we need to do is to check the current value I and j point to, are they the same, right? You remember in the previous slides, we actually mentioned if they are the same, both move forward, but we don't accumulate count. That's actually the implementation here. We check, then we don't increase. We simply let the function give us the minimum edit distance for the rest of the string and from both string 1 and string 2. So that's why we write it here. If they are not the same, then we have three options. We can either insert, delete, or replace. And our final value we're interested is the minimum value from all these three. So that's why we need to go through all these three, and all these three will call its own corresponding subproblem. And whenever we enter the next level, of course, we will check the memo if this operation has been calculate it, then this will return immediately with the result, so we don't have to go through this iteratively, right? And then after that, we save the result into memo. Just for the next time, we don't have to redo it again. This is always like a template for the dynamic programming with the top-down solution. Always that in the beginning you create this one, then at the end when you finish the calculation you save it. So that's the classic way how to solve it. That's all I want to show for today. Thank you for watching. See you next time.